So, informal quiz, not a real quiz, karma-free quiz for you, just to see where your head's at and to pull some things together from Monday. What is this? So, and I don't want you to answer out loud. I want you to come up with something, anything. What is that? So take a minute. There's all sorts of levels of answers you can come up with. Just be careful back there. Might look back. Yep. There you go. All right, everything's safe. Thank God. Okay, somebody got something for me. What is that?
An integral?
Ooh, good answer. It's an integral. Tell me more. Somebody else tell me more.
Intervals from 0 to 1.
No. What kind of integral is it? Definite integral. It's a definite integral. And there is this other kind. There are not definite integrals. We'll talk about those probably next week, maybe even this week. What else is it? So this is good. Hey, Joshua, say something.
The answer is 1 over 2?
What's that?
The answer is 1 over 2?
It is. The answer is 1 over 3, yes. What does that 1 over 3 represent? Joshua's had calc before. Right? Is that right? Okay, good, okay.
Sum of the area underneath the curve.
Under y equals x squared.
Between 0 and 1.
Beautiful. From 0 to 1, it is that area. Cool. What else is it?
Antiderivative?
No, definitely. Let's not get there. I don't want to put that up and confuse people, but yep, that is. Well, that's a this week kind of thing, I think, maybe today. Yeah, it is. How do you do, how did we get to this? Where does this symbol come from? Where did this come from? So you've got this like S.
Sum?
It's a sum. It comes from a sum. What kind of a sum? A Riemann sum. Hell yes. All right, now we're talking. So we had this process, and this is what this is all good stuff. This was great. But I want you to think of this in a couple of ways. Remember how at the beginning of the class we had derivative is instantaneous velocity, is slope of the tangent line. So this is all the things that we've said. It is this area here between x squared and the x-axis. It is a definite integral from 0 to 1. The answer will be a third that we'll be able to do very soon. But it is also a process. It's that process of cutting up into rectangles, finding that approximate sum, that Riemann sum. So it is this sum here, or it's this process where I'm going to take, let's see here, I equals 1 to n, the function at some representative point, delta x of I. And what this means is that I've got my function here, I'll just draw it again, and I've cut this thing up into n pieces. So remember how this goes. Cut interval into n pieces. What was that called? Partition. We partition it into the n pieces. So this is partition. Absolutely. And then we choose a representative x of I star. from each subinterval. And then we add up, we add up the area of n rectangles. So that was where we went through here and we were like, okay, I've got here's x1 star, here's x2, and x2 star could even be at the end, the right end, x2 star, maybe x3 star, and so forth. And then I use that representative, I go up to the curve and use that as my height, and the base of it is the width of that little subcut. So this guy here, I went up like that. This guy here, I went to the curve, and that's the height of my rectangle. And I do that all the way across, and I get a bunch of rectangles, add up their areas. So this is the height of the ith rectangle. What does this represent? Yes, what about the interval? You're right, it does. What is it about the interval?
The equal distance between?
Yeah, the distance, the width of the interval. Yes, exactly. So let's make this little note right here of the rectangle. So each rectangle has area, f at x sub I star. This is its height. And then delta x sub I star, this is the width. And that can change. It may or may not be the same for each. They don't have to all be the same. We add these all up, so that's this part right here. This is the sum of those rectangle areas, base times height, add them up. And then let the number of rectangles go to infinity. And when we do that, we get the precise area under that curve. And we represent it like this. So this thing here, in general, this goes to the definite integral from a to b, f of x dx. This part becomes the dx as it goes to nothingness. This goes to just f of x. This is what becomes your integral sign. And in fact, but kind of these two together become your integral sign. The lower limit is where you start, the upper limit is where you end. So here we're running from 0 to 1. This one right here represents a picture that looks something like this. So I got good old f of x right there. If this is x equals a, and this is x equals b, then it's that area right there. It's all about areas. So I want to kind of do this process for this guy, and I never did get to that. We talked about it. This is what I said I want to find. Joshua ruined my story and told us the answer is 1/3, but it's still a good story. You didn't ruin it, really. I'm just giving you shit. Because nobody knows, well, unless you've had calc and you know how it is. But let's do it the hardcore way. Instead of taking a jet plane to 1/3, we're going to walk the trail and pay attention to the scenery. So let's find, and you only have to see this once, but every Calc 1 student of mine has to watch this process because it's just so freaking cool. All right, so let's find this. Step 1, we're going to cut the interval 0 to 1 into n equal pieces because it just makes life a lot easier for this. So let me just show you. Let's see, here's 0 to 1, here's 0, and here's 1. If I cut this into n pieces, how big is each piece? Yep, like that, yep. How big? What's the formula? Yeah.
1, 0?
Well, so if I cut it in half, how big would each piece be? If I cut it into 2 pieces, a half. If I cut it into 3 pieces, how big? A third. If I cut it into n pieces? If I cut it into 5 pieces, how big is each piece? 0.2, which is 1/5.
1 over n.
1 over n. So if I cut this into n pieces, that's hard, right, to make that leap to the general case. But if I cut this into n equals pieces, each piece will be 1 over n wide. So let's make a little picture here of kind of how this is going to go. So the first one, if I go 1 over n, that's literally 1 over n. What's the next coordinate? 2 over n. And then 3 over n. And then dot, dot, dot. I'm going to do something I didn't. If this is the, so look here, this is the first cut, second cut, third cut. If this is the ith cut, what's its coordinate? I over n. Yeah, see, I just use that rhythm. And then we go up to the end, dot, dot, dot. The second to last one is n minus 1. And then the last one was already there, but we'll just call it n. So the second to last one's n minus 1 over n. And then this guy is just n over n, which is 1. So we're just cutting that up. I'm following my process that I outlined. I just did step 1. Step 2 is I'm going to choose the representative in each interval, in each subinterval. X sub I star. So everybody's got the web work done. In the web work, you had these choices. When you were finding your rectangles and you had a subinterval, they said, well, what does it look like if you use the left endpoint? What does it look like if you use the right endpoint? And then what does it look like if you use the midpoint to find the height of the rectangles? We're going to use the right endpoint over here. So let's let x sub I star equal the right endpoint of the subinterval. And so that's actually equal to, well, look, what is the right endpoint of the first interval? 1 over n. The right endpoint of the second interval is 2 over n. So this guy right here is just I over n. Let me stop. Let me know if there needs to be any talk about this, any conversation. Okay, cool. So my function, let's see now, I'm going to add up all the areas. So I'm going to figure out the area of the ith rectangle. And then I'm going to add those all up. So the area of the ith rectangle equals the height. Let's just kind of go back to first principles. The height times the base. What am I using for the height? I'm using x squared. So we're using f of x is x squared. And that says take the point you're using, the representative, and square it. And that'll take me up to the parabola at that point. So this is my height. What is my base? How wide is each base? One over n, beautiful. Let me stop. Is this looking okay? Yeah. Okie doke. So I'm going to add these all up. I'm going to let I be 1, then 2, then 3, then 4. And I'm going to add these all up. And so when we come to do that, let's do it without the summation notation first. Let's just write it out so we can feel a little warmer about the whole thing. So adding up the n areas, what we're going to get is the first one is when I equals 1. So it's 1 over n squared, that's how high it is, times the base. That's the first rectangle. First rectangle area. Then the second one, we have 2 over n. And then we square it to take it up to the parabola times the base. This is the second rectangle and then I put plus, dot, 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 plus, I'm gonna put the ith one in here, because it's going to help write the sum compactly. I over n squared, that's the height. Base is still 1 over n, plus, dot, dot, dot. Let's go all the way out to the end. And the last one is n over n. That's 1, but I'm gonna write it that way, so note this equals 1 squared times 1 over n. And if I could add all that up, I would know what the formula is for the area. Let's make this compact. So compactly, this is just the sum, I equals 1 to n, of these things. The reason I wrote this ith rectangle term out is so I can just plunk it right in here. And it's gonna be I over n squared times 1 over n. Notice the only moving part is that I inside there. These n's never change. That's a fixed number for now. The sum reference is an I, and so that's the moving part. So the I is moving. And now I'm gonna take the limit of this thing, and I'm done. And that should give me the true area. So step 3 is take the limit as n goes to infinity. And believe it or not, we can do this. And this is really cool. So I'm gonna write it out, limit as n goes to infinity of that expression. Sum, I equals 1 to n. I'm going to simplify this a little bit. So this is I squared over n squared. Does that make sense? Just distribute the squared. I squared over n squared times 1 over n. I'm gonna write that up. You tell me if this makes sense. You see where I got n cubed? There's like an n squared, then we multiplied by the extra n. And there's only an I squared on top. Okay. The I is the moving part. This n stays the same, so I can rewrite this with a 1 over n cubed. I'm going to pull the 1 over n cubed out in front. And I just get this. That looks familiar to me, because I know we wrote the formula on the board the other day. Remember when we talked about the sum of numbers and Euler, baby getting slapped doing math? And then we talked about this formula. What is this formula? What's the closed form? I put it on the board. You probably have to look it up. I'd be shocked if anyone remembers it, but I'll give you a talkie if you remember it. Joshua, you don't want a talkie, so you're not gonna remember. Talkies are terrible. I love talkies. Do you remember it?
Not sure, but I can try.
Try.
N.
Okay, so let me get here and start transcribing. Okay, so this is n, yes.
N plus 1.
N plus 1.
So n plus 1.
Oh man.
Over 6.
Over 6. You get a talkie whether you want it or not, I guess. I'll have to open the bag. I'll come dump them onto your paper. So this is that closed form, and this is just the formula that we talked about yesterday, or Monday. And sorry, and I forgot to copy the limit, so excuse me. This should have the limit in front of it. Apologies, because that might mess up your notes. So do insert that, because we still have to do that part, but now that's all we have to do. Let's write that up over here. So this is equal to the limit as n goes to infinity. On top, I've got n times n plus 1 times 2n plus 1. And on the bottom, I've got 6n cubed. Take a minute, see if you can evaluate that limit. And don't just remember the answer. Make sure you see what the limit is and how to do it. I'm gonna put something up here that might help a little bit. If you can't quite see what that top is, you can multiply it all out. And you get that, which might make it a little easier on the two. There we go. You good? Okay. All right. That's a big mistake. I'm with you. How do we do this limit? Let me ask you a different question. How do I do it? Sophia, do you remember? Just say it. Yeah, L'Hopital's rule would work great. We could totally, let's L'Hopital it. That's great. That's one way to knock it out. Because the top goes to infinity and the bottom goes to infinity. Beautiful. So we'll L'Hopital it. If all else fails, L'Hopital it. So this is limit as n goes to infinity of 6n squared plus 6n plus 1 over 18n squared. Looks like I still got infinity over infinity. So I L'Hopital again. 12n plus 6 over 36n, still going to infinity over infinity. Last L'Hopital. Limit as n goes to infinity of 12 over 36. Hey, there's no more n's. What number is that? 1 over 3. That, my friends, is the precise area. So good job, Joshua. But it's going to become that easy for everyone. We're going to be able to do that in our head in a little bit. Not all this, not this way. This is brutal. Let's talk about how we're going to let's talk about what ties this to the previous part of the course, because none of this stuff looks like anything you busted your ass on the first part of the course. Where's the derivatives, dude? Why did we learn derivatives? Well, I'm going to tell you. We're going to tie this with the things we've already done. So, let me get a better pen for this. So let's talk about what's called the fundamental theorem of calculus. And there's two parts to this. We're just going to do part one today. Fundamental theorem of calculus, part one, says this. I ask you to find this definite integral. And remember, that is, and let's make a more interesting picture, maybe something like that. Here's B, here's A, and it's the net signed area, positive, negative, positive. What is the cumulative area? Cumulative signed area. And this is y, x, and x. So that's a great interpretation of it. And we also know that this is the process whereby I cut this up into n pieces, find rectangles, find the formula for the sum, let the limit go to infinity. You just saw that. It's a lot of work. So the fundamental theorem of calculus says, to do all that work, here's what you should do instead. This is equal to this capital F evaluated at the right endpoint minus capital F evaluated at the left endpoint And that capital F, and we heard this word came out today, I forget exactly who said it. I think it might have been Leo. Where capital F is the antiderivative. That was you, right, Leo?
Yeah.
Yeah. Is the antiderivative of the integrand little f. What does it mean to be an antiderivative? Leo, what does it mean to be an antiderivative?
The opposite of a derivative, but like
True.
the
That's a lawyer's answer.
doing the reverse steps of taking a derivative.
Exactly.
Roughly.
Go finding the thing that this is the derivative of. Just like that. So in other words, i.e. the derivative of this thing is equal to little f. So now, this is like for a table, but there's a few we can remember easily. What we need to talk about next is how to do the antiderivatives. And once we do that, it takes this whole process of sums and rectangles and areas and limits and turns it into a simple thing, just like this. So beautiful. And Joshua, this is how you did the problem, isn't it? That's how you got 1/3. So let's actually go take a look at this. So this is little f of x, it's x squared. Where, if this is the derivative of something, what power of x was it? 3, right? It's 3. So this came from, so the big F must have had an x cubed on it. But when you take the derivative of this, a 3 comes out in front. So what do I need to put out in front to balance that? So when I bring this 3 out, I want a 1 instead of a 3. What should I put in front? 1/3. So now check this out. What's the derivative? It's just good old x squared, because the 3 and the 1/3 cancel. It's like the power rule backwards. So this is my antiderivative. That's the big F of x. And this is A, and this is B. So this definite integral turns into big F at 1 minus big F at 0. In other words, 1/3 times 1 cubed minus 1/3 times 0 cubed. And that, my friends, is just 1/3. And that's cool. That took a fraction of the time. This is the kind of stuff that always just gave me a little bit of a chill, math chill, like in a good way. That this whole crazy process is that. That's just beautiful. And this is called the integral calculus. The first part of the class was the differential calculus, the method of differentiating. Now we're going to talk about the method of integrating, integral calculus. So we need some antiderivative rules. And you've got a bunch of these in the table that I gave you, or any table that you can find. So like that super math table in there, you've got these. But let's do a little table here. So if this is f of x, this is the antiderivative. So this will be the antiderivative. And really you just gotta think backwards. That's all it is, but let's start off chill. So first off, if I have x to the nth power, then look at how this worked over here. We had x squared, we bumped the exponent up by 1 and divided by the new exponent. And that's the rule we're going to put here. So the way to go to the antiderivative is to bump up your exponent by 1 and divide by the new exponent. And I'm going to write that out because you want a heuristic device like that, an algorithm in your head. So add 1 to current exponent, divide by new exponent. But I wouldn't write it as a division, I'd write it as a 1 over, so don't, In other words, this is less helpful in many ways. Put a 1 over n and plus 1 out front. A little more sophisticated, it just works out better in general. So this is called the power rule for antiderivatives. And you can check it. Take the derivative of this thing. Bring the exponent out front, cancels with that, decrease it by 1, goes to x to the n, and you just get that guy back. So it's just the stuff we're used to backwards. What would be a terrible, boy, oh shit, I divided by n plus 1. What would be a terrible n value? -1. You don't want to divide by 0. So as long as this works if n is not -1. In other words, this doesn't work for 1 over x. So 1 over x has its own rule. Whose derivative is 1 over x? Natural log, yes! Natural log, and we put absolute value on it. Yes, beautiful. Let me give you a few here. And I'd like you to just fill in the rest of the chart. So let's see, we've got sine of x, cosine of x. This one's a little too blank. Let's see what you remember. Whose derivatives are those? That's what you have to do. Think back. I'm going to run to the restroom really quick. Let me finish that up. Let's see. Let's reveal the answers there. I'll do the low-hanging fruit first. The one without the sign change. Derivative of sine is cosine. What's here? Negative cosine. Because when you take the derivative of cosine, it's negative sine. So you've got to counterbalance with that negative out in front. And then where did this guy come from? Tangent, beautiful. And that'll get us really far. And there's a bajillion others. And in Calc 2, we will study how to take these basic things and do much more complicated things with them. Think like product rule, quotient rule, that stuff. You know how you got chain rule? We're not going to get too far into that this semester. Although it does depend on how far we get. We've got 4 weeks left. Well, 3.5. So let's do some stuff. Let's find some things. one of my favorite areas in the whole world is the area under sine of x between 0 and pi. Can you find that area for me, please? You've got what you need to pull some things together. Write out the definite integral. What I'm asking for is the definite integral from 0 to pi of the sine of x. Find the antiderivative. Plug in the limits. Subtract. Get something very pretty. How many fingers is the answer? That's what your answer? Yes, that's what I was looking for. Yeah, yeah. Also forgot a really long one. So let me show you a little notation, which you might not have yet. What's the antiderivative of sine? Yeah, over there, right? Negative cosine. So I write negative cosine. You might not have this notation part down, because I haven't showed yet. Change this into a bar, which means evaluate at. So it's kind of like replaces the integral sign. It's a nice way to keep track of things. Here I'm going to put 0, and then I'm going to put pi. So I'm writing the lower and upper limits just right there. Keeps track. Then, this is a part that folks mess up regularly when they're learning Calc 1. Put in the top and put in the bottom and subtract top minus bottom. So keep that in mind. You're going to subtract the evaluated at the top minus the bottom evaluation. So in other words, this is minus cosine of pi, just that's the top plugged in, minus, use parentheses because I'm subtracting minus cosine of 0. Feels like a million years ago that we looked at this, my cosine of x graph. So cosine of pi is -1, so this is minus minus 1, minus cosine of 0 is 1. And that, my friends, is 2. And it just seems crazy that that's such a clean number. I don't know, it always just surprises me, makes me feel happy, all sorts of things like that. Let's put one more up here that I did forget. And I'm happy to take questions on that. What about this guy? Because we kind of forgot about him. Just e to the x, right? The best thing in calculus, the easiest thing to remember of all the things. Any problems here? Yes, sir.
We're forgetting the constant.
So in definite integrals, we don't do that, actually. But let me talk about what Leo's talking about. So when we don't have numbers on here, that will become something we do. But when there is a number on here, if you think about it for just a minute, Leo, it would cancel anyway, but we don't worry about that plus c. So what Leo's saying, and this is actually a very important thing to notice, is that if I adjust any of these with a constant, it just goes away, yes. So the thing to remember is that for any function, there's actually infinitely many possible antiderivatives. They just differ by a constant. Let's put a little note there. That's a good thing. Thanks for saying that, Leo. But do you see what I'm saying about the definite? Yes. So for any, because you probably lost some points in some calc class for not putting the plus C. Everybody loses some points for that if they took calc 1. For any function, there are infinitely many antiderivatives that differ by a constant. And let's actually draw a picture to kind of pull some of this stuff in here. Wow, these pens just read today. Well, they don't read. They suck. Oh, look at that. Yes. Hell yes. So let's say I had some function like this. Notice how the derivative information of this is the same as if I just shifted up by a constant amount. In fact, the derivative information for all these guys is identical. So for each function, you've got this entire family of things that preserve that derivative info when you move back toward the right. Let's do a few things. Let's just find a few integrals here. Actually, let me give you a few properties here. A few properties that are very important and useful of the definite integral. First one is that if I have the definite integral of some multiple of a function plus some multiple of a different function, so this A and B are, whoa, don't use those because I already used them. C and D, there we go, better. These are just constants, like 3 or pi or 1/5. To do this, I break it apart just like I did with derivatives. You're going to take the definite integral of this piece and combine them like this. Yes, that's right. You can pull the constants out in front and break apart the integral in this way. This property is called, or to say that succinctly, is the definite integral is linear. Linear just means you can break apart sums and differences and do the same thing to each part, and you can also pull constants out in front of the process. Another one. I'd kind of like you to maybe tell me what you think this is. What do you think the rule is for that guy? Think a picture, get a picture. Definite integral is that process is the area, right? Those are all the same. What do you think the area would be there? What's your base? Like, what's your interval? A to A. How big is that? How wide is that? Zero. It's nothing. So if you looked at this thing, there's literally no interval here. So there's no area. So your intuition about area also is going to hold true in these things, and you should exploit that when you can. So this thing here is just 0. And let's make a note. What was special about that? The top and bottom limits are the same. There's no area. Let's do another one here. That if I have the integral from A to B, and I flip the top and bottom limits, that changes the sign of the resulting output. So if I move the B down here and the A up here, what you're doing is you're kind of moving backwards. You're doing the rectangles backwards, and so all your areas will have a negative will have a negative value associated with them. So when you flip the limits, you flip the sign of the integral, and that's a good heuristic for it. Flip the limits to flip the sign, S-I-G-N, of the definite integral. Cool. I got one more I think I want to put up here. And that is this. That if I have the integral from a to b of f of x, and let's draw a little picture here. So here's a, here's b, this is y equals f of x. I'm going to pick some point between them, c. So what I can do is I can say that this total area here, which is represented by that notation over there, is equal to the integral from a to c of f of x plus the integral from c to b of f of x dx. Can you see that in the picture? So look at this. Let's call this a1, a2. This represents a1 plus a2. This is just the a1, and this is just the a2, just done separately. So you can break them apart with a point in the middle. And with this, we can do a lot. So now we can have some fun. We're going to probably practice for the remainder of the hour here. Any questions or anything? Like, I'm not sure what you meant by that, or everybody good? Okay. Cool. So, let's do some practice. Please find the following. Integral from -1 to 1 of x cubed dx. I'm going to put these up here. I'm going to put a few up here. The integral from 0 to 2 pi of cosine of x dx. And then I'll come put another one up over here. Just leave that up for a minute. Here, this third one is the integral from -1 to 2, 3x squared minus 4x plus 3 dx. Let's work them through in order. How about we just get that first one knocked out, and then, you know, I know a lot of folks in here like to keep cranking. You keep cranking. You stay happy. I'll put some pictures up here. Because you might get some answers that you're doubting. And I want you to think about the geometry and make yourself realize that the answer you think is too simple is actually completely okay. curious what you're computing there.
Huh.
Were you using your calculator on that
No,
guy?
no.
Oh, okay, all right, that's good, I'm glad to hear that. That makes me happy. Zero, first one. So. I don't know what that one is. Oh, shit. I guess I got a little overzealous. I guess I don't know what it was either.
What is this?
Thank you. Thank you. I got crazed. Yeah, that would have been a tough one, Sam, just not knowing. Thank you. Thanks for saying something, yeah. We'll talk all these, so, we'll talk about them in a variety of ways. I did set that one up to not be too bad. What'd you get on that third one?
Is here, but I'm gonna double check my.
Okay, cool. All right. Okay, you sure? Yeah, okay, all right. You'd let me know, I know. Ridiculous. Kyle, doing all right? Okay, cool. Joshua, what'd you get for that last one? Cool, thanks. I had no idea, but I'll take, that sounds right. Yeah, it sure looks like it. Joshua got a 12. Sorry, I was like putting you on the spot. But Joshua got a 12 on that last one. Others, yes. You got that. Cool. Did you get that, Sam? You got 12. You're still processing. Got it. Yeah. Kyle, did you get a 12? Yeah. Yeah. Sounds like 12. It's the Democratic consensus. sure to use parentheses on these things. Like this guy, you're gonna subtract off that whole quantity, evaluated at -1. Looking good, everybody? Feeling all right? Let's talk about these. So, antiderivative of x cubed is 1/4 x to the 4th. I raised the 3 to a 4, multiply by 1/4, evaluate that -1 to 1, and you get 1/4 times 1 to the 4th minus 1/4 times -1 to the 4th, which is also 1. You get a 0. But look at the picture. We could have maybe guessed that it was 0 if we know a little bit about functions. This function here, this y equals x cubed, has a symmetry to it. In other words, this area here is comparable to this area here, except they're opposite sign. What kind of symmetry is this? So there's different kinds of symmetry. Like here's the kind most people think about, the full, same on the left, same on the right. We see the symmetry. Do we know what this is called fold symmetry or axial symmetry. What kind of symmetry is that? Anybody know? Symmetry with respect to the origin is what this is called. So this is symmetric with respect to WRT, the origin. And what that means is that to get from one side to the other, you flip over both axes. So flip it over this axis and then this. Two folds get you there. Flip, then flip it down. Right? That first fold gets you here, and then just flip it down. Or flip down first, then flip over. So that's symmetry with respect to the origin. And then this guy here, antiderivative of cosine is sine. I evaluate from 0 to 2 pi. So that's sine of 2 pi minus sine of 0. And those are both 0. So we're good to go. What do you think this area is right here?
Equal to two on the right.
Yeah, definitely. It's equal to the sum of these two, totally. What do you think the number is for this guy? What do you think that these two add up to? 2, just like sine, right? Because sine and cosine are just shifted versions of each other. So what do you think this area is if the sum of those is 2? 1, 1, minus 2 are the areas. So just thinking, just that basic idea of that sine area. And then we come over to this guy, and I'm going to take my antiderivative using the linearity. So notice how I keep the 3 apart, and then do my work on this guy. So bump him up by 1, divide by the new exponent. Bump him up by 1, divide by the new exponent. And this one's a little tricky because that's 3x to the 0. So you could think, well, what's the antiderivative of that? Well, bump up the exponent, divide by the new exponent. So you just get 3x. So you could use that reverse power rule that we were talking about. So you get 3x. Plug in your, simplify, plug in your limits, keep parentheses. Parentheses can kill you. Keep that stuff together. How's this feeling? Yeah. That was a lot today. I feel like we just leapt forward hugely. And with that in mind, why don't we call it a day? Why, we're good. This is where I wanted to get to. I think everybody's rocking it. On Friday, we will do an in-class thing. Sound good? Cool.
What is it?
Oh, just like we're,
worksheet?
yeah, worksheet, where we work together and you can ask. No stress. Cool, friends. Nice. Good work, everybody. We're like cruising. We're doing so good.
See you Friday.
I will see you on Friday, my friend. I'll see you a lot next semester.
Yeah, you will.
Dude.